This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. I'm your host, Jeff Doolittle. This episode will explore how to balance coupling in software design. Coupling and the related topic of complexity have come up in previous episodes. For example, in episode 638, Nick Toon and Jean-Georges Perrin talked about architecture modernization. In episode 637, the topic came up when Steve Smith shared his views on software quality. And in episode 520, John Osterhout discussed his book, A Philosophy of Software Design, which also explores topics related to coupling and complexity. And today, we'll be talking with Vlad Khononov about his book, Balancing Coupling in Software Design. Vlad is a software architect with extensive industry experience working for companies large and small in roles ranging from webmaster to chief architect. Currently, he helps companies to make sense of their business domains, untangle monoliths, and tackle complex architectural challenges. In 2021, Vlad authored Learning Domain-Driven Design, followed by the publication of his second book, Balancing Coupling in Software Design, in 2024. He is also a public speaker, presenting on topics such as domain-driven design, distributed systems, and software architecture. Vlad, welcome to the show.
Hey, Jeff. Thank you so much for having me.
Really glad you're here. So let's kick it off. A lot of ink has been spilled on the subject of coupling. What compelled you to write a book on the subject?
Well, in my opinion, that's not enough ink that has been spilled on this topic, and I had to spill much more. Now, seriously, if you look at most of software engineering and software architecture books, you will find a section dedicated to coupling, maybe even a chapter, at most a chapter. So I decided that this topic is way too important, and I'll do the opposite. I'll dedicate a whole book to coupling, and there will be one chapter about everything else.
Great. So you mentioned in the book, and as we've spoken previously, the idea of complexity in the context of coupling. And this comes up a lot in some of those previous episodes as well, and in some of the books you mentioned. Do you have a different perspective on how complexity and coupling relate to each other, or maybe the definitions of those terms?
Yeah, of course. Now, when a software engineer tries to deal with coupling, the goal is usually to address complexity. So we are here for that goal, to manage complexity of our business domain and to manage the complexity of the software solution that we are designing. Of course, what we want to do is to manage it, to make sure that we can control how that complexity is going to affect the design, and of course, to minimize the accidental complexity that our design introduces to the system. So that's my overall goal for building that framework for managing coupling. In a sense, it's a way to manage complexity through the management of coupling. Now, in order to manage complexity, we need to make sure that we understand what is complexity and that we have an agreement between each other on how we're going to define complexity, how we're going to work with it. And there are many different, some of them are complicated definitions of complexity. The one that I prefer to use when working on software design comes from the Cynefin framework, from Dave Snowden. And this Cynefin is a decision-making framework. It's a framework that helps you to make decisions in different situations. Basically, what Dave says is that complexity is a function of an action and the result of this action. If you're working on a system and you want to do something, let's say you want to introduce a change and you know exactly what's going to happen following that change, well, that's not a complex system. You are dealing with something that is clear or obvious. If, on the other hand, you don't know what's going to happen, but there is someone, some external expert that you can consult, and that person will tell you, hey, if you do this, that thing is going to happen. Again, that's not complexity. In the language of Cynefin, it's called a complicated domain or a complicated system. Now, if on the other hand, you want to make a change and the only way of truly finding out the outcome of that action is to make the change and then observe the results, or in other words, the outcome can only be deduced in retrospect, then you're dealing with complexity. In our domain of software engineering, let's say that you're working on a project that is designed as a big ball of mud, or rather not designed at all,
Right.
and you want to make a change. The only way to find out what's going to happen is to make the change, observe the results, hopefully observe the results in development environment or in testing environment, not in production. Well, that's complexity. Or maybe you think that you know what's going to happen, but then you deploy it to production, and let's say a month later, you discover that there is something else that's going to happen. Again, that's complexity. That's something that we want to avoid. So the goal of my framework for managing coupling is to avoid such situations, to take us from that retrospective knowledge of what's going to happen all the way back to the clear domain, where we have at least some understanding of what's going to happen if we do something.
So to dive a little bit more into that, it sounds like what you're saying is just because something exists in a complex domain, it doesn't mean that we can't find ways to maybe move it into those other domains over time using various techniques.
Yeah, exactly. And here it's worth to differentiate between two types of complexities. One is the essential complexity of the business domain. Say you're working on a medical system or a financial system. That's not an easy system to build, right? It's complex. That business domain is complex. There is nothing you can do about it. However, the design itself that you're architecting, that's something that you can control. And here you can either introduce accidental complexity, or you can manage the complexity of the business domain and instead of accidental complexity, design a modular solution. A solution that is going to be much more predictable and much easier to change in the future.
And you just brought in a new word, which I think is great. So we've talked about complexity and coupling, and now you brought in the word modularity. And that's another word of which much ink has also been spilled and much radio time or podcast time has been spent. But talk a little bit about the relationship between those three concepts. And I think that'll set us up for where we want to take the rest of this conversation.
Yeah, sure. So again, not enough ink, not enough.
Fair. Great.
Yeah. So first of all, we have that agreement that we want to avoid complexity. The second agreement we have to make is what we want to achieve. And of course, that's modularity. So we can treat modularity as the opposite of complexity. Complexity makes the system hard to change, hard to evolve, hard to extend. Modularity, the goal of modularity is the opposite. Let's say that you're building a system. Let's say it works. It implements its current functionalities, its business requirements. Awesome. However, if that system is being used by people tomorrow, a week from now, a month from now, doesn't matter how long it will take, but they will ask for more features. So we'll have to extend it. So I would say that the goal of modularity is to extend the goals the system addresses. It should not only address the goals that are needed today, but it should also make it easier to implement the goals that might be required in the future. And of course, what I mean here is not implement all the functionalities that might be requested in the future, and that's not possible. However, reasonable changes that the users might request in the future should be much clearer, much easier to implement in the future without having that sense of going through a big ball of mud. It should be clear what you have to change and what are the changes that you need to make to implement those future goals, those future business requirements. So I would say that we have two opposites. We have complexity and we have modularity. If we are looking at software design decisions that we are making, each one of them can either take our system towards complexity or towards modularity. Where should it go? Well, probably we want it to go towards modularity, and how we can do it, probably it has something to do with coupling.
Okay, and we'll explore that more in a second. I'm curious for listeners for whom these concepts are new, can you give some specific, or maybe just one specific example of what would they expect to see? I think most people can conceive in their mind of what a big ball of mud could look like, right? There's long methods everywhere, or there's just class explosion, and there's no sense of, how things fit together. Or maybe there's 50 different Docker containers that have all kinds of complex, like who knows, you could have a distributed ball of mud. But that's easy to conceive. I think it might be harder for listeners to conceive of what does a good modular system look like? And adding on to that, what is a module? Right? Type of modularity, like it's a good thing, but like what's a module? Can you give some examples?
Yeah, that's a great question. And again, That's why not enough ink has been spilled on this topic.
I mean, we can go back 50 years to David Parnas's paper on the criteria to be used in decomposing systems into modules, but he doesn't even necessarily give a definition that still holds up today. So I'm curious what your thoughts are on that.
Yeah, so I will address the first part of your question first, and it's what is that modularity? What is that modular design that we want to achieve? So I would say that it all boils down to two things. First, let's say that you have a new business requirement that you have to implement, or maybe a change in an existing one. You want to know exactly what is the place in the system that has to be changed in order to implement that. That's the first part. And the second one is when you are going to make the change, you need a certain level of confidence what's going to happen following that change. Again, you don't want those surprises in production a month later, right?
Right.
So for me, that's the goal of modularity. It all boils down to where to change and what the effects of my change are going to be on the rest of the system. I don't want to be surprised.
Okay, so my experience would be I know where to go to make a given change, as opposed to, I guess the counterexample is it could be everywhere and anywhere, and who knows, right? That's the complex system where only after I take action can I see the effects. But I guess, can you give some specific examples of I walk into a code base and it's modular? What am I going to see? What am I going to experience? How is it going to help guide me to knowing where I should make change? And I'm sure it's different for different languages and frameworks and things like that, but maybe give listeners some flavor of what they should expect to see. And maybe there's different levels of modularity that you could discuss as well. What are the kinds of things they would expect to see in that kind of a well-designed system?
Yeah, and that takes us to the second part of your previous question about what is a module.
Ah, yes.
Because there is so much misunderstandings about what a module is. There are so many different interpretations. One that is really popular nowadays is that a module is a logical boundary, a boundary within a service or within a physical component. For example, in .NET it's a namespace, in Java it's package, etc. And then there is this definition of a component, which is a physical boundary. Here we have boundaries of services, of systems, all those deployable units. However, I will ask you until the end of this podcast to forget about these definitions, and instead I will do what you suggested. I will rewind the time 50 years back and talk about how modules were defined way back then, when that term modularity and modules were just introduced to software engineering. And back then, a module was defined by three criteria. The first one is a module should implement some well-defined functionality, which means if you're looking at some boundary, you can describe what it's doing. What is the functionality that is implemented within that boundary? Second, that boundary should expose a public interface through which the rest of the system, its other modules, can execute that functionality. So we have public interface. That's the second criterion. And finally, the third one, and it's the most, I would say, important one nowadays, is that a module should have a potential of being independently compiled. The potential should be there. Now, it doesn't mean that we should compile it independently. That means that if we are looking at a service or a microservice, does it fit that definition? Well, if you can explain what is the functionality implemented by that service, it has public interface, and it is already independently compiled, awesome. We can say that this is a module. Now, if you look into its internal structure, and let's say that it's implemented in C#, because I love C#. In C#, what you will find there is a bunch of namespaces. Now, each namespace has a name, and it has some functionality that is implemented within it. Can you describe it? Let's say that the answer is yes. Awesome. Does it have a public interface? It does. Awesome. Can it be independently compiled? Yes, it can. So we can call a namespace a module as well. Within that namespace, we'll find a bunch of objects or classes. Each one of them has functionality that is implemented. We can describe it. Yes. It has public interface. Yes. Can it be independently compiled? Yes. Should it be? Depends, but the potential is there. So a class or an object can also be defined as a module. We can zoom in even deeper. Let's say that we're looking at a method within a class. Does it have a well-defined functionality? If it does, awesome. Public interface, we have that signature through which that method can be called. Can it be independently compiled? Well, in many languages, it can. Probably it shouldn't, but you can do it. So even a method can be called a module. So what we're getting to is that modules are fractal. There are different levels of abstraction. We are used to this term, levels of abstraction or layers of abstraction, doesn't matter. As Dijkstra famously said, the purpose of an abstraction is to create a new semantic level in which one can be absolutely precise. So we have different levels of abstraction with different types of modules within each one of those levels. Now, going back to our first topic of complexity, each one of the layers or levels of abstraction manages complexity. The level of detail of the business domain or implementation details that it uses in its definitions, in the definitions of its public interfaces, for example, is going to be different. But the goal is there on all the levels to manage complexity. So, going back to your previous question about what should you expect, what are those modules? So, the answer is modules can be found at different levels of abstraction. All of them should manage complexity in a fractal-like hierarchy.
So summarize again the three elements that make up a module, just to make sure it hits home with listeners.
Yeah, first one is well-defined functionality. Can you describe what a module is doing, or you're going to resort to, for example, reading the implementation details? If you have to read the implementation details, you don't know what it's doing. What you're describing is how it is doing that. You're not describing what it is doing. That's the first point.
That's a good clarification too, right? Because that kind of means, in a way, it's a black box. It's something that I can describe what it's going to do without necessarily needing to know the details of how.
Yeah, exactly.
So that's number one. Okay.
Yeah. Going back to that wonderful book, Philosophy of Software Design, that you mentioned in the introduction, I love how the author defines what makes a good module. One that compresses all the knowledge about the implementation details into a short and easy to express way of saying what that module is doing. What is the function of it? What is the functionality that it implements? As opposed to, for example, as I mentioned, having to read the implementation details, or maybe you will say that this module is doing that, and that, and that, and that, and that, and a bunch of unrelated things. That's also problematic. That goes against the definition of a module.
It's actually helpful you bring up John Osterhout, who wrote that book. And just to give listeners a visual picture in their minds of what you're describing, he talks about deep versus shallow modules. And this is going to relate to the second piece of the definition that you gave for modularity. So you can envision in your head a very wide rectangle that's very shallow, and it has a lot of connectors on top. That would be a shallow module that doesn't provide a lot of functionality, and it exposes a lot of its internal details through a very broad API, right, with maybe lots of methods or lots of interfaces or whatever it might be. A deep module is going to be more like a vertical rectangle with a shallow surface with few connectors, but it's going to have rich and deep functionality below it. And I think that helps guide into that second piece of a module you talked about, which is a public interface. And while public interface is the important part of that second part of the definition, I think another important part is, what does that public interface look like? Because it may be more or less helpful depending on how well it aligns with what Dr. Osterhout talks about in his book.
Yeah, so here I have to resort to the default answer. It depends.
Yes, okay.
It depends on the level of abstraction you're working
software
on.
architects. Yes.
Yeah. If you're working with, let's say, services or microservices, then the interface is going to be, let's say, a web API, a REST API, or the events or messages that are consumed or published by that service, synchronously or asynchronously, all the way it interacts with its environment. If you're on the other end of the spectrum, let's say that you're looking at a method, then the method's signature is its interface. That's how external components or external methods or modules can execute its functionality. It can be private, locked in within its object, or it can be public. It depends. But it has to provide a convenient, easy to understand, and well-defined way to execute its functionality. whoever needs that functionality shouldn't be reading through its implementation details to figure out how to use it, right? That's the goal.
Okay. So we've revisited the first two components of the definition of modularity. And what was the third again?
Yeah, and the third component or property that a module should have is that potential of being independently compiled. Now, why it's important? Well, the potential should be there. If it's not there, it means that that component that you're looking at, that potential module, is not really a module. It cannot be compiled, deployed, tested independently of some other things. So probably they should be treated as one boundary, as one module. That's why that third criteria is important here. The potential of being independently compiled.
And would that be partially because if it can't be independently compiled, that there's some form of coupling that maybe we need to be addressing that we've maybe missed?
Yeah, there is something that forces you to always work on those two, I don't want to say modules, let's say two components together at all times.
Okay, great. So I have in my mind this spectrum. On one end, I've got complexity, which according to your definition is things that I can't know the effects until I've taken an action and then observed the outcome, as opposed to things where someone may know what's going to happen or I know it because it's clear and obvious, right? So that's complexity. And then on the other end of the spectrum, I have modularity. And I wonder if other authors or other people have different perspectives. Like, is modularity the only way to deal with complexity, or what are your thoughts on that?
Yeah, so look, my thoughts are based on my experience, right? Experience that was tested in the battlefield. And my experience says that yes, that's the only way. That's the only way that works. Now, when I am presenting on this topic, sometimes people do disagree with me about when I'm saying a design decision can either take you towards complexity or towards modularity, and people say that no, a system can be both. It can be modular in some places and it can be complex in some areas. And that's correct. However, if you're making a design decision, let's say that you're introducing a new module, a new boundary, a new method, new interface, etc., I still claim that that decision can either take you towards complexity or towards modularity. Yes, the overarching system can be both. It can be complex, it can be modular at the same time because some of its parts are designed in different ways. That's true, of course. However, if you're looking on that level of design decisions, I would say that either complexity or modularity.
And I think that makes sense because to extend your thought there a little bit, I could have an implementation that's complex, but if the public interface is simple and hides the integrator from that complexity, then that's kind of where there could be that dance between the system having both complex parts and modular parts. Is that kind of what you're implying there?
Yeah, absolutely. As Eric Evans said, not all of a large system will ever be well designed. There will be parts that are not business critical, that are not mission critical, that, yeah, it's okay to round corners there. How to identify those areas? I hope we'll get to this topic in this podcast.
Yeah, we'll definitely want to get there. And can you provide a real world example maybe of what would be the problem, say, if I tried to perfectly design every single aspect of something in the real world? What would be the impact of that instead of maybe cutting some corners here and there?
Yeah, well, what's going to happen is if you're a startup company, well, you're not going to deploy anything. As a startup, what you want to do is to address complexity in the business domain, that essential complexity. Let's say you're a startup company and you want to provide a solution for your customers, people that you hope are going to be your customers. So you want to solve one of their problems. You hope that you understand what is the problem that they need help with, and you hope that your solution is going to address that problem. Will it? The only way to know is, sorry, that's complexity. If that would be easy, everyone would be doing it. So you have to do it and to observe the outcome. That's complexity in the business domain. And to get that feedback, yeah, you need to cut corners. If you're not going to do it, your competitors will, and they will get to market much faster than you are. So we have to balance our desire to build beautiful systems that are well designed and modular and, the real world where sometimes it pays to cut corners.
Well, and I think of even like a construction project sitting here in my home and you in your home. I imagine that there are some tolerances about just how close, say, the stick framing in my wall is. And if somebody was so precise down to the millimeter, that would have increased the cost. It would have, slowed things down. It would have been way overdone. Instead, we just cover over with sheetrock and we move on, right? And we're like, it's good enough. It does the job and it solves the problem of structure. So it doesn't need to be designed to that perfect level of detail, right?
Yeah, well, don't get me started on my home because so many corners were cut here.
Oh, yes. You can't cut too many corners, which we want to avoid. But let's not go there. You can go back, listeners. I mentioned at the top of the show, Steve Smith on software quality. We can revisit that one. But in the meantime, let's go back to coupling, which of course is the hallmark and the highlight of your book. So as the book continues, you take some previous models. We talked about previous ink that was spilled, right? You take some previous models for identifying coupling, which it'd be great if you can say what those are if listeners are interested in going back and seeing the history of this conversation all the way back to Jordan and Parnas and all of these different people from way back in the day. So there have been models for identifying coupling, and you've come up with a new approach. So what issues did you see in the previous models, and how is yours different?
Yeah, so first of all, why coupling? Well, once we have those opposing properties, something that can be either complex or modular, then there is something in the middle that is shared by both of those properties. Something that if we learn to control, then we're going to control the outcome. And in my opinion, that's coupling. That's how we're going to design coupling. So what is coupling? In simple words, if two things are coupled, it means that they're connected. If you have one method colon R1, they're coupled. There is a connection there. Two objects, same thing. Two services, if they are integrated in one way or another, they're coupled. So, first of all, coupling is not something that we can eliminate from our design. Like that slogan of, let's decouple everything. Well, you can do it, but you're not going to build any system without those integrations, without those connections. So we need that coupling. So we cannot eliminate coupling. What we should do is to look at it and to understand how those connections can be designed. What are those design decisions we can make about those connections and how they're going to affect that overarching system and our stress levels in the future when we will have to change them. And the first thing that we should look at is knowledge. Let's say that we have two modules that are integrated with each other. Doesn't matter what those modules are. At this point, let's say that anything on any level of abstraction, doesn't matter. They can be two methods, they can be two services, two systems, whatever. In order to work together, they have to know something about each other. At the minimum, they have to know what is the functionality that is implemented by the module that I want to call, that I want to execute, right? Or maybe when I am using its public interface, by using that public interface, I'm getting some knowledge about its internal structure. For example, what is the model of the business domain that is being used there internally? Or maybe there is no public interface at all. Or maybe it's there, but, I decided that I have a smarter way of integrating, like going straight to the implementation details and using them for integration. Let's say that both of us are implementing microservices, and as we all know, microservices should be integrated through public interfaces. There are APIs. Say, okay, Jeff, your public interface is amazing. However, give me your database. I will take whatever I need and make some changes there, and that's it, right?
If only no one would ever do that, but it happens all the time. Yeah.
Yeah. So that part of knowledge that is being exchanged whenever we have multiple modules that are integrated. That knowledge can be knowledge of public interfaces, of integration contracts, or it can spill some knowledge about its internal structure, the knowledge about the functionality that is implemented by a service. By the way, let's say that we have two services that are not integrated. In any way, we have a system with two components that are not integrated, not aware of each other at all. However, they implement the same business rule or the same business algorithm. So we have that knowledge of the business domain that is duplicated in both components, in both modules. Let's say that they're integrated wirelessly or something. That knowledge is duplicated and there is no explicit interface through which that knowledge flows. when that knowledge will change. Well, guess what? One of them is going to be changed for sure. The second one, the question is when it's going to be changed. So yeah, that's the first aspect of coupling. What is the extent of knowledge that is being exchanged across coupled components, across integrated components? The more knowledge we are going to exchange, well, the more cascading changes will follow. If we minimize the knowledge, we are minimizing cascading changes. If, on the other hand, we are maximizing the knowledge, well, we are maximizing cascading changes. Going back to the example of two microservices, tomorrow, you're going to change the schema of that table that your microservice manages, and I'm using it as, impolite way. Let's define it that way. In a sense, I am introducing dependence on your implementation detail, as if I'm saying, okay, whatever you're going to change in your implementation details, it has that huge potential of causing cascading changes in my service. So you make a change, best case scenario, you tell me that you made a change, you shouldn't do it. So instead, you're going to deploy your changes, and then suddenly my service stops working in production. I have sleepless night, and then I find out, okay, that table schema was changed. So yeah, let's introduce a corresponding change in my service. So that part is knowledge. Now, going back to your question about the history of that notion of coupling and how it was introduced to software engineering. So there is this methodology called structured design. They started working on it in late 60s. First books were published in early 70s, and it was like a domain-driven design in those days. And that methodology introduced a way to evaluate coupling. The model that was introduced back then was called module coupling. It had 6 levels, and those levels were defined following programming languages that were popular back then, like COBOL, Fortran, and other fun stuff that we are not really familiar with nowadays. And let's be honest, we don't want to be familiar with nowadays. So it had levels like data coupling, stamp coupling, control coupling, external common, and all the way to content coupling. Now, these levels basically describe what I just said, those different types of knowledge that can be exchanged across boundaries of modules. The problem with that approach nowadays, not back then, I'm not saying that that approach is bad, no, it was awesome. However, nowadays, it's really hard to use it because, first of all, people are not familiar with Fortran. People are so lucky nowadays, right? So in order to understand what's the difference between common coupling and external coupling, they have to understand what these keywords and those languages mean. That's problematic. It also had 6 levels, and some of them kind of described same things. However, because of the ways those programming languages were defined, they had to have separate levels. Now, nowadays, we don't really need that. That's why in my book, I introduced a different model that is called integration strength. That integration strength has only 4 levels. Basically, these 4 levels simply adapt those 6 levels from structured design and make them way easier to understand nowadays, to remember them, and to use them. So instead of data coupling, what I'm saying is contract coupling. If all your modules know about each other is integration contracts, awesome, that's a contract coupling.
These would be the public interfaces and the public data contracts exposed by those interfaces, correct?
Yeah, exactly. Yeah. Stamp coupling, it's basically about models. Let's say that you have a model of a business domain that is used in your service, and you're exposing that model. Cool. Whenever you will change or whenever you will have to evolve that model, well, as long as it's exposed across the boundary, that change is going to affect whoever is using that public interface. So instead of stamp coupling, let's call it model coupling. We have that model, that knowledge of a model that is being exposed across the boundaries. Next, we have control, external, and common coupling, which can be called functional coupling in our world because basically what they're describing is knowledge of functional requirements, the functionality that is being implemented by the modules. And then we have content coupling in a structured design, which is basically about introducing dependencies on implementation details. Instead of working with public interfaces, you integrate through use of private interfaces or other implementation details. So let's call it intrusive coupling. It's going to be easier to understand and easier to use. So overall, we have 4 types of knowledge. Knowledge of integration interfaces, contract coupling, model coupling, functional coupling, and intrusive coupling. 4 levels. So that was the model that was introduced in 70s. Now, in 90s, a different model for evaluating coupling was introduced by Miller Page Jones, and it is called connaissance. And this one is way more detailed. It provides a more granular types of knowledge that can be exchanged across boundaries of objects. This model was oriented more towards object-oriented programming paradigm. Now, which one is better? Structured designs, module coupling, or connaissance? Well, there's no point in trying to draw parallels between them, like what this level in structured design means in connaissance, or which one is better, which one should I learn. It makes no sense because they're describing different things. Structured design's module coupling, and as a result, integration strength, describes types of interfaces. What is the type of knowledge that is being exchanged? It's important because, well, as we're going to discuss, it's important to evaluate the amount of knowledge that is being exchanged, exposed across the boundaries, how we're going to evaluate it, how we're going to weigh it, like what are the units, kilograms or what, pounds? We don't know how to do it right now. So instead, we can differentiate between different types of knowledge. If we have model coupling, we know that it shares more knowledge than contract coupling and less knowledge than functional coupling or intrusive coupling. Now, connaissance can still be very useful for looking deeper into the complexity of that knowledge within that each type of those interfaces. So in my model, in integration strength, I'm using those adapted terms from structured design to differentiate between 4 types of knowledges. And within each one of them, you can evaluate the degree of each level. And you do it by using a subset of the model called connaissance. So in a sense, we had those 2 models. We had module coupling, 70s, then we had connaissance, 90s, and now we have integration strength that kind of combines them and adapts them to our world, makes it easier to use them.
So you've summarized for us how those previous models of defining coupling have been brought together and simplified with your model as it relates to knowledge sharing or what you call integration strength. Is there another aspect to coupling that you describe that can help people to sort of conceive of how to design their systems and manage coupling?
Yeah, absolutely. So that aspect of knowledge sharing or integration strength is only one dimension, one of 3 of the ways coupling affects your design. The second one is the dimension of space. So you are sharing knowledge. Is it good or bad? We don't know because it depends on other factors. One of them is that physical distance through which that knowledge travels. Let's say that we have 2 modules sharing knowledge about their functional requirements. So we have that functional coupling between them. Is it good or bad? Well, it depends on the distance. Let's say that those modules are microservices. So we are sharing quite a lot of knowledge between them. That means there are going to be quite a lot of cascading changes. Is it good or bad? Probably not something that I want in my design, so it's not going to be good. On the other hand, let's say that those 2 modules are located close to each other. Let's say that those are 2 classes within the same namespace, and they have to share that knowledge. There's no other way to implement them because that's how that system is defined by its business requirements. In that case, well, yes, they're sharing knowledge. Yes, there will be cascading changes. However, they're close to each other. So when those changes are going to happen, that cognitive load that I'm going to experience is not going to be that high as if I have to modify 2 microservices simultaneously. No, they are located close to each other within probably the same folder, maybe even the same file. So I know that I have to change those two things that are located close to each other. That change is going to be something that is pretty obvious how to make it and what its effects are going to be, right? So we have that dimension of space, that distance through which that knowledge has to travel to reach its destination. Now, once we have those two dimensions, we can already talk about interesting combinations of two values. Let's say that we are minimizing the knowledge that is shared across the boundaries. So we are limiting ourselves to sharing only the knowledge of integration contracts, and that's it, without spilling any details about how our modules are implemented internally. In that case, if we maximize the distance between them, what we get is a system with modules with quite an extensive distance between them. And it's okay because they're not going to have to change together. We're minimizing those cascading changes by minimizing the knowledge. Great. Now, what if, as I mentioned a minute ago, what if we cannot minimize that knowledge? Sometimes we do have to share in that knowledge of functional requirements, or we have to use the same model of the business domain, or maybe even implementation details. Who knows? Sometimes we can find ourselves in those situations. So let's assume that we are sharing lots of knowledge. In this case, what we can do to manage the cognitive load that we will experience in the future is to bring them close to each other. If we do that, we have high amount of knowledge, low distance. In other words, this relationship describes high cohesion. We have things that will change together. They have to change together because of those business requirements. There's no other way around it. So we're making our lives, our future lives, better by bringing them close to each other. So that when we'll have to change them together, they will be close to each other. It will be easier for us to implement that change. So again, that first relationship, low knowledge, high distance, this is what we usually call loose coupling. The opposite one, high amount of knowledge, low distance, is high cohesion. Now, what if we'll have both of them, both of those properties or those dimensions have high values? Let's say we have high amount of knowledge shared across high distance. Well, guess what is going to happen in your future? Those two modules will change together whenever there is a change in the business requirements. And each of those changes will have to propagate across the whole system towards other components that are integrated with it. So we will have to chase those distant components, distant modules all over the place, and to modify them together, forget about some of them, discovered in production, etc. All the fun stuff about living with a big ball of mud, So that's complexity. The cognitive load that you will go through to evolve that system in the future is going to be insane. That's complexity. Now, a bit counterintuitive relationship is the opposite one. Let's say that I have two modules or a number of modules that are not sharing much now. Let's say it's either the lowest level contract coupling, or maybe they're not even integrated with each other, so that shared knowledge is zero, basically. And I'm going to put them close to each other. So both aspects, the integration strength, that shared knowledge is minimized, and the distance between them is minimized as well. And when I'm doing conference talks on this topic, I usually ask the audience. So let's vote. Who thinks this is a good design? Who thinks it's a bad design? And usually it's a draw.
It's 50-50.
Yeah.
Well, in my mind right now, I have like a utils or a helpers project in my mind where you're just like a grab bag of everything. Is that kind of what you're saying?
Yeah. You know what? Let's get back to that topic of utils and helper in a few minutes.
Okay, great.
For now, let's talk about more of business critical stuff.
Okay.
Let's say business functionality.
Great.
Business objects, not related to each other, and we put them close to each other. Is this good or bad? So on the one hand, it sounds okay-ish because, yeah, they're not going to change together. We're minimizing that knowledge. Great. However, that's a tricky question because if we only have two modules, then let's be honest, who cares? But in a real project, those things are not limited to one or two. They are rather growing towards infinity. So let's say you have a dozen or maybe 100 of unrelated modules located close to each other. the distance between them is low, they are not going to change together. But your future self will have to change one of them in the future, right? And when we were talking about the goal of modularity, that it should be easy to understand where the thing you want to change is located. Suddenly, we are getting back to that cognitive load, because now we are looking at that bunch of things that are shoehorned into the same boundary, and you have to find the one that you have to modify. So again, we have cognitive load. So again, we have complexity. So this relationship, when both values are low, introduces complexity as well. So overall, if we're looking at integration strength and distance, if they have opposing values, one is high, the second one is low, that design takes you towards modularity. If their values are equal, let's say both are high or both are low, that design takes you towards complexity. And you know what? Let's talk about the third dimension. And the third dimension is the dimension of time. So the first one was strength, that gravitational pull when components have towards each other. The second one is the dimension of space, the distance through which knowledge has to go. And the third one is the dimension of time. Now, why this one is important? Let's say that I have two modules with intrusive coupling between them. And these two modules are two systems. That means we have quite a high distance between them. And we also have quite a lot of knowledge shared between them because of intrusive coupling. That's another tricky question I love to ask at conferences. Is this design necessarily good or bad?
It depends.
Sure, of course. Yeah. So let's talk about what it depends on. So let's say that that's the way I'm designing the interactions between my business objects in part of a system that implements some business critical functionality. Well, that's bad, right? However, on the other hand, let's say that we have a legacy system, and you know how legacy systems work. They work. How? Nobody knows. They just work. They're not going to change because nobody has that courage of touching them. But sometimes you do need to interact with them. You need to take some information, maybe some data from those systems. Well, if that system is defined as legacy and it's not going to change, then, well, I don't care. I can introduce that intrusive coupling. I will go straight to its database and take whatever I need, right? Because nobody is going to change that schema. And that takes us to that dimension of time or volatility. How frequently our components are expected to change. If we're talking about something like a legacy system or like that utils namespace or those helper objects that are just a bunch of string-related operations that are not really going to change that frequently, hopefully, it's okay to tolerate some complexity by putting them together. It's okay to introduce that intrusive coupling to a legacy system because of low volatility. Now, how can we evaluate volatility? How can we analyze that system and make that decision that, yeah, it's okay. Here, we're not expecting much of changes. Well, there are different ways we can do it. There are different models of predicting the future. The one that I prefer as a domain-driven design fanboy is domain-driven design's subdomains. Basically, the idea says that if you're looking at any business domain, you can identify three types of business subdomains. You will find core subdomains that are describing some core business functionality, something that is business critical. If you make a mistake there, well, troubles are going to follow. And the opposite of a core subdomain is a supporting subdomain. Supporting subdomain is something that you have to implement, but it's not business critical. It's something that, let's say you need some CRUD data entry screen. It's boring, right? Implementing it's not interesting. It's obvious how to implement it. There is no complexity in that business domain, and business is not really interested in evolving its functionality in the future. Like it's not going to affect the company's bottom line in any way. So if we are comparing those two already, core subdomain and supporting subdomain, core is going to change much more frequently because it's all about that competitive advantage of the company. And the business is interested in optimizing it over time. So there will be much more changes in core subdomains than in supporting subdomains. The third type of subdomains is generic subdomains. And if previous two, we have to implement them ourselves, generic subdomains are something that somebody has already implemented for us. It's all those areas, those complex problems that it's not worth trying to solve yourself. You just use some product that implements that functionality, and your competitors are going to use it, and nobody cares, and it's not going to affect your bottom line in any way. So those are generic subdomains. That generic solution that you are using, will it change? It might change. That implementation within the boundary of a generic subdomain might change. Maybe there will be security fixes or new versions, etc. So there will be some volatility there, but that's a solved problem. So we are not really interested in trying to solve it. We are looking more at core subdomains and supporting subdomains. One is interesting problem, the second one is boring problem. Interesting problem is going to change way more frequently than the boring problem, a supporting subdomain. So that's the model that I prefer to use to evaluate volatility levels. Now, in the book, I go much deeper into other things that can also affect volatility, because poor design can make your supporting subdomain quite volatile. If, for example, you have a supporting subdomain, business-wise, it shouldn't change that frequently.
Can you give an example of a supporting domain that might fit this concept?
Let's say that you're implementing a marketing company that offers an innovative way of optimizing advertising campaigns to make them as profitable as possible, to show the ads in the most effective way on the cheapest ad spaces, etc. For that system, its core subdomains are going to be all about that optimizations, right? However, you still have to manage your advertising materials, like those banners you're going to show, or those landing pages. So you need some CRUD data entry screen for that creative catalog. Is that interesting? No. If I'll design it better, will it make the company more profitable? Will it make it easier to optimize advertising campaigns? No. So that creative catalog is going to be a supporting subdomain, whereas optimizations, that service that the company is providing or it is promising to provide to its customers, it's much more about its core subdomains.
So we've explored these three different dimensions of coupling. You've talked about integration strength, which is measured in how much knowledge two modules share. We've got distance, which is the amount of sort of space, we can kind of think of it that way, between these different modules. And then we've talked about volatility, or how subject something is to changing over time. Now, if you can kind of just bring that all together for listeners, because it's a lot, I think, in an auditory format to kind of hold together. And of course, get the book, read the book, right? All that's all great. But can you bring it all together for listeners here as we come to the end of this episode?
Yeah. So first of all, if we're looking at integration strength and distance, if we put XOR, exclusive OR, between them, then we can express complexity and modularity. Modularity is strength, exclusive OR, distance. If the values are different, great, you have modularity. They're equal, you have complexity. As we mentioned in the introduction or in the first part of this podcast, sometimes it's okay to round corners. Sometimes it's okay to introduce complexity. So we can extend that formula and we'll put that relationship between strength and distance in parentheses and say modularity or not volatility, which means if volatility is low, it's okay to have complexity, to have both strength and distance to be either high or either low. However, if volatility is high, then make sure that one of them is high, either strength or distance, and one of them is low, because then what you're doing is you're helping your future self to find that place you have to change, and you're helping yourself to predict what the outcome of that change is going to be.
I appreciate a couple times that's come up, cognitive load and the idea of not hating your future self. So that's great. Is there anything else you would hope listeners would take away from this episode, or any closing thoughts?
Well, I would say that coupling is way too important. Any design decision that we're making, it doesn't matter what is the level of abstraction we are working on, it doesn't matter what is the type of component we are working on, or what is the language we are using. Even if you're looking at something that some people might not consider a programming language like HTML, I would say that strength and distance are there as well. So whether you're going to read my book or a different book, I would say make sure you understand how coupling affects your systems and how it affects the cognitive load your future self is going to experience.
If listeners want to learn more, where can they go or what should they do?
Yeah, so I spent over 5 years writing that book, Balancing Coupling in Software Design, put my soul into it. I think everything I know, we try to condense it into those 300 pages. Yeah, they can follow me on Twitter, on Blue Sky. My handle is Vladik. My blog is vladikk.com, which is kind of not really alive lately, but
you can go update it before we publish the episode.
Let's be honest, I'm not going to do it.
Okay. All right. That's fine. Well, Vlad, thank you so much for joining me on the show.
Thank you so much, Jeff, for having me. It's a pleasure and an honor being here.
This is Jeff Doolittle for Software Engineering Radio. Thanks for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.